NASA's Artemis program intends to establish the first long-term presence on the south pole of the moon. In order to achieve this ambitious goal, infrastructure must be in place on the lunar surface to ensure astronaut safety and maximize scientific return. This requires transporting potentially large and heavy equipment and habitat structures from lunar landers to their intended destinations. This year's NASA Rascal competition called for innovative designs of a lunar surface transporter vehicle capable of achieving this functionality. Our team addressed this requirement by designing LEDA-1, the Lunar Equipment Transporter 1. This mission design includes both a full-scale conceptual vehicle and a scaled-down limited functionality prototype. The LEDA-1 mission begins launched aboard the SpaceX Starship commercial lunar lander. With a usable payload fairing of 9 meters in diameter and 18 meters in height, and a mass capacity of over 100,000 kilograms, this commercial launch vehicle is the only major in-development launcher capable of carrying a vehicle this size. After landing on the lunar surface, the vehicle deploys from its stowed configuration and offloads its first cargo onto the lander's pulley elevator system. Per the Rascal competition guidelines, the vehicle is required to carry cargo up to 15,000 kilograms in mass, 4.57 meters in diameter, and 7.8 meters in height. This mission requires the safe transportation of these payloads across the lunar surface to distances over 1,000 meters away from the lander. This journey is aided by a variety of instruments and sensors, including optical cameras, laser distance sensors, star trackers, sun sensors, IMUs, strain sensors, and load cells to ensure the cargo arrives safely at its destination. The vehicle again uses the onboard crane system to offload and deploy its payload at the base location. Finally, LEDA-1 returns to the lander to hibernate and recharge at an external charging station in preparation for its next cycle of surface operations, which it will repeat for the next 5 years to help establish necessary infrastructure for a long-term human colony on the lunar surface. The conceptual design features a scalable, deployable crane based on NASA Langley's lightweight surface manipulation system. Additionally, this design uses a scissor hinge deployment mechanism, which can be expanded and contracted from 5 to up to 11 meters in length to stow the vehicle during transit and accommodate different sized payloads. The mobility system utilizes shape memory alloy spring tires and heavy-duty brushless motors. Each major component was analyzed using FEA and ANSYS to determine deformation and stresses under required load conditions. The goal for our physical prototype was to create an accurately scaled down, limited functionality vehicle representative of the conceptual design's mechanical systems in order to test the functionality of the combined crane and mobility systems and the dynamics of the vehicle while loading and transporting payloads. An Arduino Mega receives user input wirelessly and sends signals to the motor controllers, which then actuate the drive, crane rotation, and winch brush motors. These systems are powered by an onboard 12-volt, 20-amp-hour rechargeable battery. Since the functionality of NASA's LSMS crane system has already been demonstrated, a simplified jib-style crane was created using 1/4-inch thick aluminum tubing welded in the AME machine shop, pulley wheels, and an off-the-shelf cable winch. The crane was mounted onto a circular aluminum plate with heavy-duty shelving brackets to help resist the moment created by picking up heavy payloads. Since the crane is the component that is bearing the loads, FEA was critical to determine the feasibility of our simplified design. Due to time and budget constraints, a unique approach to developing a rotation system for the prototype crane was used, which integrated a drive motor, a bike sprocket and chain, and a lazy Susan bearing. The crane mounting plate could be fastened directly to this mechanism for smooth rotation under a wide range of loads. The wheel subassemblies utilize custom aluminum parts, machined, welded, and assembled in-house to integrate the drive motors, rubber tires, and coil spring suspension. The vehicle controls are programmed in C++. The operator can control the vehicle via a custom-made GUI or command line inputs sent to the Arduino either remotely using Bluetooth or directly via USB. Before integration, extensive subsystem level tests were conducted to verify the structural integrity of the crane and the chassis and the controllability of the mobility system. With nearly 800 components, including fasteners, the integrated prototype weighs in at about 65 kilograms with a length of 2 meters, which is consistent with the scaling from the conceptual design in its extended state. The system functions mechanically as expected, with the ability to drive forward and backward, rotate the crane 360 degrees, and actuate the winch to lower and raise the cable. Accounting for the dimensional scale factor and the difference in gravity, the maximum payload capacity requirements for the prototype on Earth's surface are 15 kilograms, 1.4 meters in length, and 0.8 meters in diameter. To test the dynamics of the integrated system, payloads of different masses were first lifted at various crane angles on a flat surface. The prototype was capable of lifting 5, 10, and 15 kilograms in 45-degree increments, covering the full 360 degrees around the crane, without risk of tipping. Additionally, the system was capable of lifting well over our mass requirement, at 21 kilograms from 45 and 90-degree angles. The final integrated system-level tests involve combining the functionalities of the crane, structures, and mobility subsystems to load, transport, and offload a 15-kilogram payload in rougher, sloped, outdoor terrain. These tests were also carried out with a larger payload to represent the maximum volume case, which took up most of the length of the extended support structure. Although the functionality of the prototype was limited, the conducted tests helped verify the dynamics of the integrated system to ensure tipping will not occur during loading or offloading, and the vehicle can secure the payload during transportation. Between the conceptual design, FEA simulations, and system-level testing of the prototype, our team successfully designed a robust vehicle in its early stages, capable of meeting the requirements. Since the prototype could lift well over the requirements, future iterations could focus on lightening the vehicle, while still maintaining the mechanical and dynamic requirements. Overall, the LEDA-1 system has so far proven to be feasible in achieving a critical functionality for establishing a permanent human presence on the Moon.